Hello, welcome to this lecture. This is lecture 10, and we're still talking about advanced statistics. And the subject is still analysis of variance. We have discussed one-way ANOVA, we have discussed two-way ANOVA, and today we're going to look at a special case of two-way ANOVA. And it involves a particular design blocking. That's special because we don't touch very often on design in this course. So it is about design. And blocking, in its turn, touches upon the next subject of the course, that's the next lecture, and that is analysis of covariance. And they are both techniques for increasing the precision for comparison between treatments. So that's what our next two lectures are about. All kind of tricks, either in design or in the model, to get a more accurate comparison between the treatments. Let's see. It doesn't work again. We'll take this one. And that one doesn't, yeah. Okay, so we're going to discuss so-called block designs. And such a design allows for a more accurate comparison between treatments than a completely randomized design. I hope you remember that so far we randomly assigned treatments to units. But that's going to change today. Now, when we moved from one-way ANOVA to two-way ANOVA, we actually took the sum of squares for treatments from one-way ANOVA, and then we made a split into three sums of squares, one for main effects for effector A, one for main effects for effector B, and one for interaction. So instead of one sum of squares for treatments, we all of a sudden had three sums of squares there. Now, again, compared with one-way ANOVA, we are not going to make a split of the sum of squares of treatments, we are going to make a split of the sum of squares of error. We will take out part of the sum of squares of error, and it will become the sum of squares for blocks, and there will be a new and smaller sum of squares of error. We say that we are filtering out part of the error variation. You will see what it is about in due course. But this is sort of the preview of it all. Okay, as an example, we take a field experiment. That's very classic actually, because statistics, of course, has most of its roots in agriculture. We want to compare the yield of 3 potato varieties. And we have a field at our disposal to do so. And this field is divided in 12 smaller pieces called plots. And what we want to do is we want to grow the 3 different potato varieties on these plots, and after some time harvest, and the yield is our response Y. So the question is, how do you assign the different potato varieties to the plots? That's a design matter. You have to decide what goes on plot 1, what will go to plot 2, etc. Okay, let's see. A first option is to do it in some systematic way. The advantage of that is, of course, that if you do it systematically, it's less easy to make a mistake. And one way is to go through the field column-wise. So we fill the first column up with A and 1A in the next column, and then 4 B's and last 4 C's. That's one way to do it. And you could do it like that. And the other option, you can guess, would be to do it row-wise. So first row has the A's, second has the B's, and the last has the C's. Also an option. But which would you prefer? I hope you think that you would prefer neither, because so far we decided upon randomization. We randomly assigned A, B, and C to the plots, such that we have 4 A's, 4 B's, and 4 C's. And here you see a possible outcome of randomization. Now, what is randomization about? we talked about it briefly before, randomization is basically there to avoid confounders. And here is an example. Some time ago, I think a couple of years ago, in the news, there was a lot of fuss about eating bacon and sausages. It was supposed to increase your risk for bowel cancer. And there was a warning involved against eating many sausages or a lot of bacon. And that was in a report of the World Cancer Research Fund and also the American Institute for Cancer Research. So they're big institutes. Nevertheless, if you looked into the evidence, it was surprisingly flimsy. The reason is that you cannot take, say, 20 people and randomly assign 10 of them to a life of bacon and rashers and the other 10 to something more healthy, and then see at the end who has got bowel cancer and who has not. And that's not possible, fortunately. What you can do is you can take 10 people that already eat bacon and rashers more than most people, and you can take 10 people that don't and then compare them. But the problem is, if you find a difference at the end in their health, if you find that in one group there is more bowel cancer than in the other group, let's say that the sausage group has more bowel cancer, is it really due to the sausages, or is it maybe due to the fact that these people have other life habits than the more healthy food people too? Maybe the people that eat a lot of sausages and rashers take less exercise, less fitness, maybe they smoke more. So it's quite possible that at the end it's something else that is responsible for the higher incidence of bowel cancer. And the problem is, of course, that in such an observational study you cannot randomize. Randomization was advocated by Fisher in agriculture and by Bradford Hill in medical research. So it is to battle confounders. In an observational study like with the sausages you cannot, but in many other studies with plants, with animals, with more harmless treatments, you can randomize, and you do so. So randomization seems to be the answer here. But as you will see, it actually is not quite. Okay, so with a systematic design, treatment differences may be confounded with systematic differences between units. If you go for the row design with A in the first row, B in the next row, C in the last, and for one reason or another, maybe prevailing wind direction, the first row gets more wind than the last row, any differences you find are confounded with differences between rows. That cannot happen with randomization, of course. Also, if you randomize, the assumption of independent error terms epsilon in the model is supported as well. So there's a lot to say for randomization. And so far, we randomized all the time. That is a particular design called a completely randomized design. So far, at most instances, we used this completely randomized design. And in the field experiment, the experimental units are the plots, the treatments are the varieties, and these varieties are randomly assigned to the plots. At least that's an option. Now, suppose that we indeed use the randomization, and this is the result. Okay, so we have fairly and squarely randomly assigned the A, B, C to the 12 plots, and this is what we got. And we know that there is a gradient in fertility. Let's say that on this side there are more fertile plots where plants grow better, and on this side there is less fertility where plants grow poorer. Maybe there is a canal here, there are lots of canals in the Netherlands after all, and these plots are wet and these plots are dry. Now this is the result of randomization, but if you look at it, you start getting worried, because A is on this side, mostly on the dry plots, when there is a canal here, and B, on this side, closer to the canal, is on the wet plots. So if at the end you find a difference between A and B, is it really a difference between the two types of potato, Or are the two types the same, and are you seeing that plants on dry plots grow differently from plants on wet plots? The problem is that you have randomized, but the randomization seems a bit unfortunate given that you know that you have wet and dry plots. Of course, you could randomize again and again, but yeah, is it really random at the end if you have to try so many times before you're happy with your design? There is a much better thing you can do. You have extra information, the gradient in fertility or the wet plots versus the dry plots, and you should use that information in the design of the experiment. You will see that it solves the problem about unfortunate randomization, and at the same time it will give you a more accurate comparison between treatments, what you call a win-win situation nowadays. So we have worries about the design, and we're going to solve that by including the extra information, namely that we have a gradient in fertility, or that in that direction plots get wetter, closer to the canal. Okay, what do? We group the plots. We make 4 groups with 3 plots in each group. These groups are called blocks, and here they are. Here, in dark gray, you have block 1. In light gray, you have block 2. In orange, you have block 3. In green, you have block 4. And then you randomly assign your potato varieties within each block. So you have A, B, and C randomly assigned to do the 3 plots here. A, B, and C randomly assigned here, here, and here. So instead of one big randomization, like in the completely randomized design, we have 4 randomizations here, 1 separate randomization within each block. And you can see that the design now is quite a happy one, because we have A, B, and C on dry plots, but we also have A, B, and C on wet plots. The worries about the outcome of randomization are gone, because we only randomize in this direction and no longer in that direction. In that direction, in the gradient in fertility direction, we have put the blocks. And the idea is now that the variation in this direction, the gradient in fertility or the wetness of the plots, is captured by blocks in the model, you will see, and the remaining variation between plots within the blocks, that's about the error terms at the end in the model. You will see. So we have 4 randomizations instead of 1. And we'll get a more accurate comparison between treatments. Intuitively, I hope you already see that, because we are comparing A, B, and C on dry plots, but also we are comparing A, B, and C on wet plots. All the time we have A, B, and C on plots that are similar. So that suggests that we get a more accurate comparison. This design is called a randomized complete block design. It is randomized because we have a randomization within each block. It is complete because each treatment appears in each block, and usually in a randomized complete block design, each treatment appears once within each block, like in this case. Okay, so RCBD, that is our new design. Now, what is a block in general? It's a group of similar, homogeneous, experimental units. So you can group plots with similar soil condition, either being wet or dry, for instance, in a field experiment. But you can also have maybe some research going on with people. People are the units, and you may group them. May put people with a similar physical condition in the same block, in the same group. Or when you work with batches of compound, and there is variation from batch to batch, you make sure that all the treatments are compared with the same batch. So you have, if you compare 3 treatments, 3 portions of batch 1 with the 3 treatments, 3 portions of batch 2 with the 3 treatments, etc. You will see some more examples of blocking in this lecture. Okay, and the idea is that treatments are randomly assigned to the units within each block. So they're randomly assigned within each block to similar plots, to similar units. Okay, in a randomized complete block design, each treatment appears an equal number of times, usually once in each block. And in that way, a randomized complete block design is balanced because each combination of a block and a treatment occurs an equal number of times. So you don't have any worries about what type of sum of squares to use. You get the same results with type 1, type 2, or even type 3, which we did not discuss. When you have missing values, it's another story. When one of the plots becomes so wet that nothing will grow there, all your potatoes rot away, then you won't use that observation, probably. You get an unbalanced design, and then it matters again which type of sum of squares you use, and the rule of thumb is still the same. You use type 2. The model, nothing new there, basically. You have the Yij here on the left. That's the yield for the ith treatment, that's the ith type of potato, in the jth block. And we write it as a base level plus a treatment effect tau I, a block effect beta j, and the usual error terms epsilon ij. So it's tau because it starts with a t from treatment, and it's beta because it starts with a b from block. Yeah. And commonly we have a single observation per treatment per block, like in the example, but if we have more, we have to add a k here and here to number the number of repeats of the same treatment in the same block. This is an additive model, as you already know. So no interaction is involved between treatments and blocks. It's not, there are no terms tau beta. Actually, they're hidden in the error terms over here. How does it work out with sums of squares? Well, you already know about an additive model. So we have a sum of squares for treatments, a sum of squares for blocks, a sum of squares of error, and they add up to the total. Total number of observations minus 1 is degrees of freedom for total. For the treatments, it's 1 less than the number of treatments. For the blocks, it's 1 less than the number of blocks. And if you add these two together and subtract from n minus 1, you can show with a little bit of mathematics that the error sum of squares is receiving b minus 1 times t minus 1 degrees of freedom. So it's the same as before. First you take the total minus 1, then you put down the degrees of freedom for the effects, in this case for treats and blocks, and if you subtract, what is left is for the error part. Now, in a one-way ANOVA, there is no sum of squares of blocks. So basically, these two together, the sum of squares of blocks and the sum of squares of error here, are the sum of squares of error that you would have found without blocking. So part of the sum of squares of error in a one-way ANOVA without blocking is now put into a sum of squares for blocks, and a smaller one remains. And again, the variation in the direction of the gradient, in the direction of weather plots, is now captured by the sum of squares of blocks. It's put aside, and the variation that remains is between plots in the same block. And since these plots are similar, we have taken care of that by making the blocks ourselves. We hope that variation is so much reduced that we get a much better impression about the differences between the treatments. And since we remove part of the sum of squares of error, we say that we are filtering out part of the variation of the residual error. Okay, what are interesting tests? Well, the most interesting one, of course, is the test whether the treatments are different or not. Null hypothesis is they are the same, and you hope that you will reject. And that's the aim of the experiment, to find differences. The test statistic is the mean square for what you're testing, treatments, over always the mean square for error. That's the one you will look at first. But you can also test for differences among blocks, all the betas being 0 or being the same. Remember, with the cornerstone representation, you can take the first level, say, as the reference, so the TOR1 is already 0, so all the TORs the same. If you have TOR1 is 0 already, is all TORs 0. Same story for betas. Test statistic, you're testing blocks, mean square for blocks, over always the mean square for error. Why do you look at that test? Well, you would be rather disappointed if it was not significant, because you have taken a lot of effort in the design to make these blocks. And if you put wet plots in one block, dry plots in another block, you expect to find big differences between these blocks. And if this test is not significant, it indicates that you could just as well have done the experiment without blocking. It was a waste of effort then. So you hope that this test is significant as well, because it means that all the trouble you have taken, all the effort to make this design was worthwhile. Okay, another example. We talked about sections of highway before when we introduced one-way ANOVA. Remember, we had the panes, reflective panes, that we wanted to compare 4 reflective panes. Now you can imagine that if you want to compare these reflective panes, you have a number of segments of highway, sections of highway at your disposal, and you notice, after you have randomly assigned your panes to your sections of highway, that pane number 1 is predominantly assigned, just by chance, to sections of highway with a lot of heavy lorry traffic, while pane number 3, just by chance, is assigned to pieces of highway sections where there are not many lorries. So at the end, if you find a difference between panes 1 and 3, is it really the difference between the panes, or is it because unfortunately pane number 1 had it a lot harder with all these heavy lorries than pane number 3? So it's basically the same story as with the wet and dry plots. Instead of plots, we have segments of highway, and instead of wet or dry, we have heavy lorries or not. So again, instead of randomization, we can first group our segments of highway and take 4 sections with, let's say, heavy lorry traffic and randomly assign the 4 panes to these 4 sections. Then take 4 sections with less heavy lorry traffic, also similar for that reason, and randomly assign again, etc. So you can make blocks, groups of sections again, sections that are similar with respect to concentration of traffic that passes, heavy lorries, etc. And then you assign within each group. So our reflective paint example could be improved by blocking as well. So what would you have then? You would have the panes as one experimental factor with 4 levels, the locations of the sections of highway as another. Same location means same amount of traffic. And again, you will have an additive model, and this time the treatments are the panes, and the blocks are the locations where I've got my 4 sections of highway for each location, where the panes are randomly assigned to these 4 sections within each location. Yeah, that's another example. So I hope you get a feeling now that blocking is something you can do pretty often, and it can be quite useful. You will see. Okay, you have seen blocking before. You didn't know, but in the first week we had paired observations. The most extreme example I think in the book is with twins. Paired observations are basically blocks of size 2. Yeah, and with paired observations we used a paired t-test. If you handle paired observations as if it was a block experiment, so you write down an ANOVA model with blocks and treatments, the f-test for treatments is actually the square of the paired t-test, and you get the same p-value with the f-test as you get with the t-test in week number 1. So it's not as if you have to rock your brain whether to use blocking with ANOVA to test for differences or a paired t-test. When you have blocks of size 2, they will give you the same results. Here's another example. It's from the book. Yeah, the terminology is a bit unfortunate. I'm sorry for that. It's the terminology of the book. I'll explain. We want to compare 3 insecticides. And we have groups of 100 seeds, yeah, that are put in the soil. And what we observe after a while is the number of seedlings that emerge. So if you are totally out of luck, none of them will emerge, 0. And if you're a very fortunate person with green fingers, all 100 seeds will emerge. Now the idea is that with the insecticides battling the insects, there will be more seedlings emerging, and you want to compare the insecticides and probably use the one that gives you the highest number of seedlings emerging. Yeah, that's the idea. Okay, now we have 4 plots here. That's an unfortunate terminology. So better think about the plots as 4 separate pieces of land, say. I could change the story also to 4 different trays with soil or so. But let's say 4 pieces of land, different locations. And you want to compare your insecticides. Well, you know that it is possible that on one piece of land there may be more insects than on another. If there is water close by and it is shaded, there will be more insects. If another place has more wind, and the wind direction may determine whether there are more or less insects. So from one piece of land that we have to another, there can be big differences in presence of insects. So what you do is you put your groups of 100 seeds of string beans within each piece of land, and you apply your 3 insecticides within each piece of land as well. So the pieces of land are the blocks. So you don't use only one insecticide on one piece of land. No, you take care that all 3 insecticides are used on groups of 100 seeds within each piece of land, so that the insecticides are compared on groups of 100 under the same conditions for that piece of land. So this time the TORs are the insecticides, the betas are the plots, the pieces of land, they are the blocks. And you have your insecticides as the treatments and your plots, the pieces of land, as the blocks. What do you see? Well, first of all, we look at the insecticides, and it's a very low p-value, so clearly at least 2 of the 3 insecticides are different with respect to each other. And we also see that there are quite some differences between our blocks, our pieces of land, so probably it was a good idea to have the 3 treatments, the insecticides, within each plot, each piece of land. Okay, since we know that the 3 insecticides are different, our next step would be to find out whether they're all different or whether maybe 2 are the same and different from the third. So we're going to make pairwise comparisons next. And we could do so with Fish's LSD. It would also be possible to use Tukey. That's all what we discussed before. There is a slight intermezzo here in between to make you sit and think. So I'm going to raise some problems, then I'm going to ask you to stop the video, to think about it, and come back. Yeah? You can take a cup of coffee or tea or even stretch your legs or so, but think about it as well. The data are between 0 and 100, because I've got 100 seeds, so there will never emerge more than 100 or less than 0. Yeah, you cannot have anything negative. So basically, the data are percentages, 50 out of 100, 50%. Would that make you worry about the normality assumption? And would that make you worry about the equivariance assumption that you make in analysis of variance? There's a hint. Think about what happens when an insecticide has a mean close to 0 or close to 100%. For instance, compared to another insecticide that may have a mean close to 50%. Okay, so stop the video and spend a few minutes thinking about this. Even if you don't exactly know the answers, the fact that you have spent some time thinking about it means that you will probably better understand what I'm telling you next and will see why other possibilities are less likely. So try to rock your brain a little about this. See you in a moment. Okay, welcome back. Here we go for the answers. First of all, should we worry about the normality assumption? The answer is yes. You see, the normal distribution extends all the way to the left and the right. It has no lower or upper bound. But if your data touch strongly upon 0 and 100, that's not well represented by a normal distribution. On the other hand, if most of your data are, let's say, between 20 and 80%, the fact that the normal distribution extends beyond that is not much of a problem. The thin tails won't bother you anyway. But if you can get close to 100 and close to 0 with your data and you use a normal assumption, it's even possible that when you're close to 0, that you would get, in more complex models at least, a negative fitted value, which would be embarrassing, of course. So normality is something of a worry. A bigger worry is actually the equivariance assumption, because if you approach 0, you hit the lower bound. So variation has to become smaller. If you hit the upper bound, 100%, variation has to become smaller as well. But in the middle, around 50%, you have a lot of arm length. A lot of variation remains. So you expect insecticides around 50% to show more variation in their outcome than insecticides that have lower or higher mean percentage. So percentages are worrying when you want to tackle them with an ordinary ANOVA model. There are actually other models which are not part of the course that you can use here. Okay, back to business. I already accidentally showed you the slide, this one. We have seen that blocks are significant. But we know that small differences for big data sets can also be significant, but since they're small, they're maybe practically not so important. So in general, you wonder, how valuable is blocking? Can I express the advantage of blocking in a number? You can. That number is here. It's called the relative efficiency. I'll explain in a moment with an example, still with the string beans, with string beans and seeds emerging from string beans, what it is about. First of all, how do you calculate this efficiency? B is the number of blocks, T is the number of treatments, mean square for blocks, mean square for error. You can pick them from the ANOVA table. You plug in the numbers, you calculate. Now, before I explain what this is about, let's calculate it first. So for the insecticides, you have 4 blocks, B is 4. You can pick your mean square blocks from the ANOVA table, 146. Let's have a look at that. This 146, okay? You have to pick your mean square error also from there. So let's give me this again. So blocks 146, mean square error, well, that's here, 4.33. So 146 is the mean square for the blocks, plots here, 4.33 is the one for residuals, that's the error. So you can pick the two numbers from your ANOVA table. You plug in the 4 blocks and the 3 treatments, 3 insecticides, and what you get is 9.9. What does it mean that the relative efficiency is 9.9? It means that if you don't block, if you take a completely randomized design instead, you need 10 times more observations to get the same precision, the same accuracy for comparing the treatments, in this case insecticides. So with blocking, your comparison becomes 10 times as accurate or if you like, with blocking, to get the same accuracy as with a completely randomized design, you need only 10% of the amount of observations you need for a completely randomized design. So you can either save on observations, which is nice when it is an animal experiment and treatments are rather awkward for the animals, or you can increase precision by blocking, which is also nice, of course, because you get a more accurate comparison, you get more narrow confidence intervals for differences between treatments, and you know much better where you are when you have to decide what treatment to use in the future. Okay, so relative efficiency tells you with a number how well blocking works out, whether it's really worthwhile. There is an alternative. This formula I showed you, well, let's go back for a moment. You can see this formula over here. It is in a book by Cochrane and Cox, and the derivation is far from simple, so we're not going to do that. But there is an easy alternative. Cox, by the way, was Gertrude Cox. She was the first woman in statistics. Okay, a rough and ready alternative, which I think is intuitively more appealing. What you do is you fit both the randomized complete block design and the completely randomized design. So you take your data and you fit a model with the blocks and a model without. The model without is just a model with the treatments. That's the one-way ANOVA. And the model with the blocks is, of course, the blocking analysis that we are discussing now. From each of the two fits from R, you save the mean square error and you take the ratio of the two. So the ratio of the one under completely randomized design and under the randomized complete block design. The mean square here will be bigger than here because blocking takes out part of the error variation after all. This is intuitively, I guess, more appealing because the MSEs are the estimates for the error variance under both situations, and you're simply checking by this ratio how much the error variance is reduced by introducing blocks. If you do it here with the insecticide example again, well, we need the mean square error with blocking. That's the 4.33 here. We also need the mean square error without blocking. If you were behind the buttons with R, you could fit the model again without the plots and again read the mean square error. But actually you don't need to do so. You know, the sum of squares for plots and the sum of squares for error here are basically the result of a split of the sum of squares of error in a one-way ANOVA with insecticides only. So we created a sum of squares of 438 for plots by taking it out of the sum of squares of error under a one-way ANOVA. So if we go back to a one-way ANOVA, we put it back into the sum of squares of error again. So if you add these two, you get the sum of squares of error without the plots. And if you add these two numbers for degrees of freedom, you get the degrees of freedom of the sum of squares of error without the plots. And if you take the ratio, you have the mean square error mimicking the complete randomized design. And it's 51.6 that you get. So if you take the ratio of the two, you end up with 12. It's more than the 9.9 we had before, but it is of a similar order. You could say that 10, 11 times, maybe 12 times as many observations are needed without blocking to get the same precision. So blocking is really worthwhile according to both criteria, either the formula or the rough and ready way to do it like this. Okay, I told you before that when we had the significant F-test comparing insecticides, that the follow-up would be pairwise comparison. So let's briefly look at that. It's basically a recap of what we did for one-way ANOVA. To compare the three means for the insecticides, I have to calculate the least significant difference from Fisher's method. Remember, that is the number yardstick basically that you have to exceed for two means to be different. So if the LSD fits in between two means, they are significantly different. How did the LSD look like? It was a critical value from a t-distribution times the square root of 2 times the estimator of the error variance over n. The n, that's important, is practically always in statistics the number of repeats of a single treatment. So it's not all observations like some people think at the exam. No, it is the number of repeats of a single treatment. So if we take one insecticide, it appears in each of 4 blocks. So n here is 4. Each insecticide appears 4 times in the dataset. We know that the pooled error variance estimator is the mean square error, so we can take that from here, from the ANOVA table, 4.33. What about this critical value? Well, you can look in a table or use PQRS or even use R. You need degrees of freedom, and they are always from the error line, the residual line, 6, because in a t-test, degrees of freedom are always about the arm length for estimation of sigma square. So you estimate sigma square by the mean square error, so it's the degrees of freedom connected to the mean square error. Mean square error is here, 6 degrees of freedom you need for the t are there. And since this is all two-sided, you need alpha over 2 is 0.025 in the table when you go for the usual alpha of 5%. You can find the t, take some practice there because we live on paper in the exam, so you have to be able to do this, 2.447. If you plug it all in, you see it over here, you get 3.6. So any two means for two insecticides that differ more than 3.6 in absolute value will be significantly different. Now here you have the 3 means. The order from low to high is 1, 3, 2. We always order, and you start on the left and you add the 3.6, and do you exceed the 80? No, you don't. So these are further apart than 3.6 and significantly different. You go to the next one, compare with this one, also significantly different. So all pairwise comparisons are significant here. If these two had not been significant, remember you can give them a common underline or 2 little a's here. That's also done in the literature to indicate non-significant differences. So in this case, we conclude that all 3 insecticides differ significantly from each other. Yeah. On average, you have most seedlings appearing with insecticide 2. You have the least with insecticide 1, and 3 is in between. So do we always take 2? Well, it depends. We have a difference of 7 here. It would be interesting to look at the confidence interval and to see how big the difference between 2 and 3 can be. Because suppose that 2 is rather nature unfriendly and 3 is much more friendly. You could decide, although you get some less seedlings, to use 3 after all, but then you have to be pretty sure that 3 and 2, although different, are still close in the number of seedlings appearing. So as soon as cost is involved, either money or cost for the environment, it is interesting to have a confidence interval, let's say, between 2 and 3 as well, because if you have a narrow interval that suggests that the difference is sort of around 7, and you are prepared to accept a little bit less of a yield because of the environment, maybe you would use 3 after all. Yeah. Okay, here is another question raised. You're asked to derive an estimate, a standard error, and a confidence interval for the expected difference between insecticides 1 and 2. I guess, according to the previous slide, that 2 and 3 would have been more relevant, but okay, to take practice, you can do this. If you like to work on this yourself, you can stop and look at the previous slides and try to work this out. And I'm going to work it out with you together now. So you have to either stop now or stay on and look how it works. What are we interested in? We're interested in TOR1 minus TOR2. That's the difference between the treatments 1 and 2. And we want an estimate for that. That's the head, always indicating that you are after an estimate or estimator. What is the estimator or estimate? It's the difference between the two sample means. Remember, the dot means that you sum over index j, in this case over blocks. The bar means that you take the mean. So this is the mean for treatment 1 and this is the mean for treatment 2. Insecticides 1 and 2. These were the means, this is the estimate. So that's not too hard actually. Next, standard error, that's harder. We need the standard error of the estimator. Remember, a standard error is just a standard deviation. We call it a standard error because it is a reflection of accuracy of the estimator, but it is really a standard deviation as well. Any standard deviation is the square root of a variance, so we need to calculate the variance. Anything in statistics about variation always works through variances. You always get back to a variance. What is the variance of the difference between the two means? You also did this in week 1 where you compared 2 rather than 3 treatments. It's the same piece of mathematics still. These two means are independent. So the variance of their difference is the sum of their variances. Each one separately is the error variance divided by the number of observations in the mean, and since every treatment appears once in each block, we have as many repeats of a treatment as we have blocks. So that's why we divide by b for this variance and by b for that one. So the b is the number of observations in a mean. So that's 2 sigma epsilon square over b you get. We estimate the sigma epsilon square or sigma square by the mean square error from the ANOVA table. B is 4. The MSE, if you go back to the ANOVA table, I hope you remember from the insecticides, was 4.333. So you end up with 2.1665 for the variance, but you take the square root for the standard error. So to take the standard error, we take the square root and we end up with 1.4719 over here. Okay? So we have an estimate, we have a standard error, but ultimately we want a confidence interval. What about that one? Well, what are the bounds? The bounds are, at the lower and the upper bound, the estimate, minus 29, plus or minus a multiple of the standard error, that's the 1.4719. What is the multiple? It's a critical value from a t-distribution for 0.025 and the number of degrees of freedom from the mean square error, but we already looked that up before. It was 2.447. So if you calculate the lower bound with the minus and the upper bound with the plus, this is what you get. Yeah? You can see that 0 is not in the interval. That's right, because the interval contains all values that are not rejected by the t-test, and the 0 was rejected. So you can see in a glance that all these differences from minus 32.6 up to minus 25.4 are likely, on the basis of the data, for the difference between 1 and 2. They match with the data because they are not rejected by a t-test. If you would increase sample size, go for a bigger experiment, you would reject more values and then the interval would become more narrow and you would get a more and more accurate impression of the difference. Now, it may still vary between minus 32.6 and minus 25.4. If you don't think that's accurate enough, you need a bigger experiment. Okay, now, so far so good. We had a sum of squares for blocks, a sum of squares for the treatments, sum of squares for error, and a total sum of squares. We're going to make life a little bit more complicated again. Like for two-way ANOVA, we're going to look at a factorial experiment again. So suppose that our treatments actually have a structure. They are combinations of little a levels of a factor A and little b levels of a factor B. So we have two experimental factors and their combinations are the treatments. Yeah. For the moment, let's simply define one vector with AB levels. So we ignore the structure and we have AB levels. So if one of my vectors has 3 levels and the other has 4, I've got 12 combinations, and I just pretend as if I have one vector with 12 treatments in there. And I can, of course, construct a block experiment and randomly assign my 12 treatments within each block. Then I would have a sum of squares for treatments, a sum of squares for blocks. This should be blocks, not B only, I guess. One for error and one for total. And then next I can split, like we did before, my sum of squares of treatments into one for vector A, vector B, and interaction, and end up with a sum of squares for blocks. This one is sum of squares for blocks too. One for main effects for A, one for main effects for B, one for interaction, an error sum of squares, and a total. So I could have no less than 1, 2, 3, 4, 5, 6 sums of squares in my ANOVA table. Yeah? So these 3, SSA, SSB, SSAB, SB4, are from a split of the sum of squares of treatment, and these 2, the sum of squares for blocks and sum of squares of error, are actually from a split of the original error sum of squares in one-way ANOVA without blocking. Here's an example. It's about loaves of bread. Here you have a typically Dutch loaf of bread. We're interested, that's the response variable, the variable of interest, in the percentage of protein in a loaf. And we can prepare these loaves of bread with different flours. So we have an interest in comparing the types of flour. Which type of flour gives me maybe a higher protein content? And we wonder whether the comparison between the 3 types of flour will be the same for different temperatures. Are the differences between the 3 types of flour the same for different temperatures of the oven or not? So we have a vector A for types of flour, that's the vector of main interest. We have a vector B for the temperatures, and we're interested in the interaction that possibly exists between the 2. Now, this is done under laboratory conditions, and these people have just a small oven, so they cannot do many loaves a day. So what they can handle actually is a limited number of loaves per day. So the whole experiment cannot be performed in one single day. We have to spread over several days. And then, if you get a little bit more experience, as soon as you hear that an experiment is spread over several days, you think days should be blocks. Because from one day to another, maybe another batch of flour is used. Maybe another person is preparing the loaves. So there is variation from day to day. So you better have all your treatments. You have 9 of them, the combinations of type of flour and temperature, within each day. So each day you prepare 9 loaves, each loaf with a separate combination of type of flour and temperature. And you do that for 3 days, and you have 27 loaves in total. Yeah? So this is definitely more complicated than just taking one type of flour and one temperature on a day and preparing lots of loaves, and then on another day taking another type of flour, another temperature, and preparing a lot of loaves. That would be easier. But then if you see a difference between 2 types of flour, even at the same temperature, it could be a difference between the days, another person doing it, rather than the difference between the type of flour. So the days will be the blocks here. So what have we got? Well, for the moment we take 9 treatments, the 9 combinations. So we have a treatment sum of squares with 9 minus 1 is 8 degrees of freedom. 3 days, days are blocks, 3 minus 1, 2 degrees of freedom. 27 loaves, so 27 minus 1, 26 degrees of freedom for the total. 8 plus 2 is 10, subtract from 26, 16 is what is left for the residual part, the error part. And now we remember that the treatments have structure. They are combinations of flour and temperature. So we're going to split up this sum of squares into 3 separate sums of squares. One for capital A, flour. 3 minus 1 is 2 degrees of freedom. one for capital B, which is temperature. Also 3 minus 1 is 2 degrees of freedom, because they happen to have both 3 levels. And for interaction, it is 3 minus 1 times 3 minus 1 is 4. Note that 4 plus 2 plus 2 is 8, same 8 as here. So this is a split up of the treatment sum of squares, but this is a split up of the degrees of freedom. So if we replace these treatments by these 3, we get 6 sum of squares, in the ANOVA table. 5 in the table from R, because by default it will not produce the total sum of squares. You have to do that yourself. Okay, let's see. We can imagine to start with one-way ANOVA, and then we can split the sum of squares of treatments into 3 parts and the sum of squares of error into 2 parts, the sum of squares of blocks and a new SSE. So the splits we made in the previous lecture for the factorial structure and the split we are making in this lecture for the blocks, they both come together in this example. And we end up with all these different sums of squares. Let's see how it looks like for the real data. Here you have some R. So the linear model routine, this is your response variable. We have days, the blocks, main effects temperature, main effect flour, interaction, and this is where you get your data from. So that R knows when it meets up with temp, that temp is apparently to be found here. We ask for the ANOVA table. This is a name of the model. You can choose yourself. If you like, you can call it Mickey Mouse. And then you have to ask for ANOVA of Mickey Mouse, and it will give this table. Now, where do we look at in this table? Well, first of all, we have to worry about the type of sum of squares, because by default R will give you type 1 sequential sums of squares. That's what you're looking at now in the yellow box. But this is a balanced design. We have an equal number of combinations of temperature and flour within each day. So we can make do with this result. Type 1 or 2 are the same. Next step is we look at the blocks. Significant. So the first impression we have is that indeed blocking was worthwhile. There are differences between days. It's good that we took that into account. So our first impression about usefulness of blocking here is favorable. What next? Well, next we're going to look at test results and maybe pairwise comparisons. Okay, suppose we are primarily interested, as I told you before, in comparing flour types, but we included the temperatures because we wonder whether temperature makes a difference for this comparison between flour types. That's about interaction, basically. What would you conclude from this ANOVA table? Question to you. And if you would proceed with pairwise comparisons, what table of means would you inspect as a follow-up? Would you look at separate tables for temperatures and flour types, last one the most important, or would you look at a table of means of combinations of temperatures and flour types? So stop the video, think about it for a while, maybe write down some conclusions and see whether we agree when I proceed with the answer on the next slide. So see you in a moment. Okay, welcome back. Let's have a look. There is interaction between temperature and flour type. If you look here, you will see that there is interaction. That means that the differences between at least some of the types of flour are not the same for all temperatures. So if you would advise on a particular type of flour to use, you have to be careful because it could be that one type is suitable for one temperature while another type is more suitable for another temperature. We have to look into this. So interaction is important, and that means that we don't look at main effects. You only look at main effects when you can ignore interaction. As soon as there is interaction, meaning that you cannot look at flower type separately from temperature. You don't look at main effects because that is looking at them separately, and you shouldn't do so when there is significant interaction. Okay, what do? We have to look at combinations of temperature and flower type. So we have to ask R for a table of means of combinations of temperature and flower type. And then we ask R for pairwise comparisons between the means of these combinations. We can find out more about the interaction then. A profile plot would be nice as well, by the way. And also we can find out more, get a more detailed impression about the differences among our flower types. Okay, so here you have a profile plot. And if we look and let's say at this one, here you have the 3 temperatures, 1, 2, 3. And along here we have the means, that's the percentage protein, mean of the loaves, and we have connected the means that are corresponding to the same flower type. So the solid line is A, and the one with the dotted one here with the small dots is C, and the one here in between is B. And if you look at this, you know that roughly parallel lines means no interaction. So you can already guess that the interaction is probably due to this one that is different from these two, while here the differences are much smaller. So the interaction is probably located here. It has something to do with flower type C and temperature 1. And it would be important to look at your data as well to see whether there are any odd observations, outliers, because if this is not for real but just due to one observation, some loaf of bread where something went wrong, you have to be careful, of course. But let's say that it is for real. It's really a bigger difference, it appears. So it appears that this is where your interaction is coming from. Okay, pairwise comparisons. Well, here I asked for pairwise comparisons between types of flour within each temperature. Yeah. Here I've calculated the LSD, same formula as before, mean square error for the S epsilon square. And now, remember, we have 3 days. We have all treatments at each day. So each combination of a temperature and a type of flour appears once on each day. That's 3 repeats of each treatment. So that's the 3 here. Yeah. And the critical value, 2.12, well, same story as before, 0.025 for your alpha in the table, and always degrees of freedom are 16 in this case from the error line. 2.847 is the mean square error that we use here for estimation of sigma epsilon square by the pooled variance. The MSE is the pooled variance. 2.92. So any differences that are in absolute value larger than 2.92 are significant, and there are only 2 here, these 2. All the others are smaller. And you can see this is A versus C and B versus C for temperature 1. A and B versus C for temperature 1. So indeed, this is the reason for the interaction. Here, nothing much seems to happen. There's no evidence for differences here. They could be, but they seem to be small. But here, definitely something is going on that creates the interaction. Okay, was blocking useful here? Was it really worthwhile to have all these treatments within each day? Creates a horrible amount of work because you have to use the different types of flour and you have to each time change your oven to another temperature, etc. So was it really worthwhile to take all this effort? Well, we have either the nice formula from the book by Cochrane and Cox, or the rough and ready approach with the 2 mean square errors. Let's see. Blocks are days. They are significantly different, we have seen, so that at least is nice. What is the RE according to the formula? Well, we have 3 blocks. B is 3, we take the mean square for blocks from the ANOVA table, I have to admit MSB is occasionally MS for vector B and occasionally the MS for blocks. Maybe we should have changed it to blocks here. On the other hand, you have to get used to the fact that the same notation may be used for different things, that it is sensitive to context. So remember that this is about blocks. You can pick it from the ANOVA table like the MSE. Number of treatments is, of course, the number of combinations that we are looking at, 9 combinations. Yeah? If you work this out, you get 1.7. If you take the rough and ready method, you can take your MSE directly from the analysis with blocks. And if you drop the blocks, you put the sum of squares, not the mean squares, the sum of squares for blocks back into the error sum of squares. You put the degrees of freedom back to the error sum of squares, and you get the 1.9 here with the rough and ready method. So roughly speaking, if we take the average of the two, you need about 80% more observations without blocking to get the same precision with blocking. So if you do blocking and you take care that you get all the treatment combinations within each day, you are more precise than when you randomly assign your treatment combinations over days. You're almost, well, you're just some 80% more precise, or you could say you could do with 80% less observations. Yeah, so it is worthwhile. If the outcome had been something around 1.1, you may wonder if a gain of 10% is worth all the trouble of changing oven temperatures, confusing people maybe, etc. But this is still worthwhile. Okay, we're going to end up with 2 slides about terminology. And I'm going to give you a summary of the terminology first, and then we'll have a look at 2 examples. And I need some tea because I'm running a bit dry, but we're at the end, so I'll manage. Okay, a vector is basically a controlled variable, an explanatory variable. It may be qualitative or quantitative. You already met quantitative explanatory variables in regression, X variables. They're usually called X variables or explanatory variables, so it's often that the term vector is more reserved for a qualitative explanatory variable, so a variable that is actually telling you about different treatments, labels for treatments. So qualitative is often referred to as a vector, and quantitative may be referred to as a covariate. You will see next lecture as well. So roughly speaking, a vector is about treatments, and the number of treatments is the number of levels. So vector levels is the levels of the vector in the experiment. So when you compare 3 types of insecticide, you have a vector for an insecticide with 3 levels. Treatments are combinations of vector levels of vectors in the experiment. Yeah, so keep that in mind. We had, for instance, temperatures and types of flower, and it is the combinations that are called the treatments, and these have a structure, a vectorial structure, which we explore with main effects and interaction. Blocks, well, you have to make them yourself in the design phase. You cannot think afterwards, oh gosh, yeah, let's block on days, because you can only block on days when you do it beforehand, when you have all your treatment combinations within each day. So blocking is a design issue, and a block is a group of similar experimental units. And you have to interpret that broadly. It can be plots in a field that are similar because of soil condition, but it can also be loaves being prepared on the same day under similar conditions. Experimental units in an experiment where you can randomize, they are the units to which the treatments are assigned. And the measurement units are actually the units, maybe within these experimental units, which are actually measured, where the response is measured. You will see more about these two types of units in the next two examples. Replications. You always need replication in statistics somehow. It's the number of repetitions of a treatment, and the little n letter is usually used. So the number of units that receive the same treatment, that's the number of replications. And if you start with a balanced design and no observations get lost, each treatment has the same number of observations, little n. The control treatment, well, it's often there. It's a known treatment to monitor experimental conditions. If something goes wrong, you can see, because you're familiar with the control, you know what to expect. It can also be used as a sort of standard to compare other new treatments with, or it can be a placebo in medical research. When people get medication, it's better that they don't know whether they receive medication or not. There is always a group of people as a control that does not. But yeah, if you don't get any pills or powders, you know that you're in the control group, and you feel immediately depressed because nothing is going to happen with you. So the people in the control group, they get a pill, a powder, or a drink as well, only there's nothing in it. It's a placebo. Right, two examples, and we're going through them together. The first one, it's a field experiment with varieties of maize. We have 3 varieties of maize, but we use fertilizer, and we can apply fertilizer at 4 nitrogen levels. So think about fields. We have 3 fields, and in each field we have 12 plots. So each field looks like a checkerboard pattern of 12 plots. What we measure is the leaf length of plants. Yeah. And we have randomly assigned the 12 combinations of varieties and nitrogen levels to the plots in each field. So what I'm going to ask you now is to stop the video, look carefully at everything that's given here, maybe make a few notes, and then for yourself try to decide what are the experimental factors, what are the treatments, are there any blocks, and what are they? What would be the experimental units, the measurement units, and the response variable. Yeah? And by the time that you think you know, come back and we'll go through this together. Okay, welcome back. What are the experimental factors? Well, we have a factor variety at 3 levels, nitrogen at 4 levels. Yeah? And you could argue that fields are a factor at 3 levels, but they are the blocks. Yeah? So that factor is covered by the blocks. So you could mention that as a factor as well, but you should also mention that it is a blocking factor. How do you know that? Because quite carefully we have assigned all 12 treatments to the plots in each field. So what are the treatments? They are the combinations of varieties and nitrogen, 12 of them. Yeah? So don't say that varieties are treatments or nitrogen are treatments. No, it's the combinations of them, 12. And these treatments have a factorial structure. Yeah? They are a combination of a variety and a nitrogen level. What are the experimental units? Now, by definition, the experimental unit is the unit that receives, in randomization, the treatment. So what actually receives the treatment here? Well, you can see it here, a plot, a piece of land in the field. So a whole plot is the experimental unit. And from that plot, a number of plants are measured. They are the measurement units. And the response variable is leaf length. So probably in the analysis, we will have to take the average leaf length of plants in a plot that gives us a single number per plot. You cannot take the separate plants within a plot and analyze with the techniques we have discussed so far, because plants in the same plot are close together, they share the same conditions, will be alike. So there's dependence. So to avoid that dependence, you can take the average of the plants within a plot as the response to analyze. There's another example. And again, I'm going to briefly discuss. You can have a look and then we'll discuss the answer together. Totally different example. We're now producing plastic irrigation pipes. And we're interested in the quality of these pipes. And we have two manufacturing plants. A plant is a factory, not something with leaves in this case. And from each plant, each factory, we have randomly selected from the production process 12 pipes. Pipes like this. Now, these pipes are manufactured under one of two water temperatures and one of three types of hardeners. Yeah, and in each factory, for each combination of water temperature and type of hardener, I've got two replications, two pipes. And for each pipe, the strength is measured at 5 locations. So you can imagine that we take something heavy that we put on a location and we increase and increase the weight until the pipe cracks. That would be an option. Okay, so again, have a careful look, stop the video, have a careful look, think about the question about experimental factors, treatments, etc. again, and come back when you're ready. Right, welcome back. What are the experimental factors? Well, we use water temperature at 2 levels and type of hardener at 3 levels. And our treatments are the 6 combinations. They are the 6 possible ways we can produce a pipe. We have 2 plants that produce pipes. They can be different. So quite carefully, we have selected 6 pipes from each plant. Yeah, 12 pipes from each of the plants for each of the factories. So the factories are blocks, 2 blocks. Yeah. Experimental units. Well, we randomly assign each of our 6 treatments, water temperature and type of hardener, to a pipe. A pipe is the measurement unit. And what is the experimental unit? Apologies. Experimental unit is a pipe. What is the measurement unit? It's the location on a pipe. And we probably have to take the average of the 5 locations as the response of the pipe as a whole, because again, locations of the same pipe will have measurements that are alike, dependence. There are actually models that allow you to introduce the data per location. They're called mixed models, but they are not part of our course. So in our course, in order to protect our assumption of independence, we will have to take the average per pipe. Okay, that's it for today. I hope to see you back next time when we talk about analysis of covariance. Bye-bye.